Welcome to today's webinar, StreetSmart, brought to you by GPS World. I'm Joelle Harms from North Coast Media, digital producer for GPS World magazine, and I will be your event manager. Before we get started, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars and will be emailed to you tomorrow. At this time, I'd like to acquaint you with the ways in which you can participate during today's presentation. Please notice the Submit button in the lower left-hand corner of your console. Just type the text box at the bottom left, then click Submit to place your question in queue. We encourage you to ask questions throughout the presentation. Our Twitter feed is placed on the right-hand corner of your screen, and you can use the hashtag GPSWorldWebinar to submit any additional questions during the webinar or to enter into discussion with other attendees. You may learn more about our speakers by viewing their photo and bio on the left-hand side. And if you're logged into any social media accounts, you can share the webinar's title, description, and URL with your friends or colleagues on popular social media sites. A PDF file of the slides can also be viewed on the left-hand side. You will also be emailed a PDF tomorrow. If you aren't already a GPS World magazine subscriber, we'd like to invite you to sign up today for free. All you have to do is click the GPS logo in the center at the bottom of your screen and fill out a short form. Finally, if you experience any technical difficulties during today's event, select Help to submit your issue, and assistant producer Bethany or I will personally assist you. Now I'd like to turn today's event over to our moderator, editor and publisher of GPS World and Geospatial Solutions, Alan Cameron.
Thank you, Joelle, and welcome everyone to today's webinar, StreetSmart, City Modeling and Other New Geospatial Techniques in Urban Mapping and Navigation. Today's webinar is related to the cover story in the July issue of the magazine, which was also titled StreetSmart, but was in a slightly different area of this general field. That article by 3 Japanese researchers, Lee Tatsu, Shunsuke Miura, and Shunsuke Kamijo, covered 3D city mapping and modeling for positioning with multi-GNSS and explored some new techniques in one field of endeavor. Today we're going to look at today's webinar is not at all a repetition of that story, but an expansion and amplification of certain common themes in this area. We're going to be looking at the data collection and processing for 3D mapping, and then the better quality or higher accuracy GNSS positioning that can be done using that 3D mapping. We have 4 presenters today. 2 of them are from University College London, Claire Elul and Paul Groves, both lecturers at University College London. And then we have Rahul Gupta from Spirent Communications and Gregory Moura from a French software company called Octal Synthetic Environment. And we'll go in this order: Claire, Gregory, Rahul, and Paul. Claire is going to discuss the collection of data, Rahul and Gregory the processing, and then Paul the use of that 3D data. We'll start with Claire Elul from University College London. Claire is a lecturer at the college, and she specializes in 3D GIS, in particular the identification and rapid querying of topological relationships between objects in 3D within spatial databases. Claire, the floor is yours.
Thank you very much, Alan. Just to sort of clarify the topological databases thing, basically that is finding out if things are next to each other or inside each other. So that's sort of putting it in more lay terms, I suppose. What I'm going to do just for the next 10 minutes is allow everybody who's listening to dip their toes into, I guess, how 3D city models are created. Starting by giving just a one-slide hook into how to quickly describe a 3D city model, looking at the traditional way of creating a citywide model that would be perhaps done by a national mapping agency such as the Ordnance Survey in the UK, but also looking at other sources of 3D data that might be actually more easily available to people than via national mapping agencies. And just to conclude, some open research challenges in 3D GIS or 3D Geographic Information Science, essentially. So to start off with, quick hook into how to describe a 3D city model. We have a standard called CityGML, which is a standard under the Open Geospatial Consortium, who are the standards body for GIS, essentially, the ISO for GIS. Which describes 3D city models with 5 levels of detail, where a level of detail describes how much how close to reality a particular model is. So as you can see from the slide, level of detail 0 is just a flat Earth 2.5D, it's called model. 1 is cube, 2 you add the roof structures, 3 you add more details about dormers and windows, and 4 actually contains details about inside the building as well. So that's we find it a very useful hook to describe 3D cities. So when you're looking at 3D data sets, this is a good way to describe them. In practice, what you'll actually find is that many 3D data sets are mixed level of detail. So you might find some important buildings, such as Big Ben in London, will be described at level of detail 2 or 3, but then a row of houses in the suburbs will be described at level of detail 1. So, having said all that, if you are a national mapping agency, like I said, such as the Ordnance Survey in the UK, the way 3D data sets are created, you essentially start from a 2D data set creation process called photogrammetry. So this is how traditionally people have been creating maps for tens, if not hundreds of years. And the idea behind photogrammetry is that you send an airplane up to take photographs using a special camera of your city or country if you're the National Mapping Agency. And the photographs must have a 60% overlap along the line of flight and 15% along the sides. And you use that overlap to create stereo ortho photos, so 3D photography, essentially, by using the overlap to identify common points and creating the 3D images. And what you can see on the slide is on the left-hand side, there's a standard aerial photograph without the orthophoto, and it's very difficult to tell what the top and the bottom of the building is and to actually create a 2D map from it. But when you've got the orthophoto, you can actually create a reasonable looking 3D image, and you can actually identify the top and the bottom of the building far more easily. So then what you do is there's some software which can automatically process these photos, not 100% automatically, but semi-automatically, let's say, to create a standard 2D map, such as the one you might find even in a Google map. So that's the 2D mapping. And once you've got the 2D map, what you can do is essentially use a process called extrusion, or growing the building, to create a 3D map from the 2D. So you've gone from a 3D orthophoto to a 2D map and back to 3D by growing the buildings to a particular height. It's a very good way to rapidly create a 3D model of a whole city if you've got 2D mapping, and 2D mapping is quite widely available these days. So you can essentially say, I'm going to grow all the buildings to 10 meters in height if you don't have any additional height information. Obviously, the problem with that is that 10 meters in height is not a realistic representation of the variation in height of buildings within a city. So what you would ideally do is use another source of information to actually identify the real height as close as possible of buildings. And The most useful source of information for doing this is a source called light detection and ranging, or better known as LiDAR. And again, this is something you capture the data by flying an aeroplane and fire rapid pulses of laser light at 150,000 pulses a second from the plane to the surface, and then measure the bounce back time. So you have a sensor that measures the bounce back time of all those pulses and creates essentially a cloud of points from the distance measurement. So every time it hits, for example, the roof of a building, it will create a point in the LiDAR point cloud. And the higher quality and more dense the laser beam, the more detailed the resulting point cloud is going to be. So on the top right of that slide, you can see LiDAR point cloud from the UK's Environment Agency, which has a point density of 25 centimeters. So you can see how dense it is. And from that point cloud, you can then derive the building height of individual buildings within your city model. The trick, however, is that if your point density is 25 centimeters between points, obviously if you've got a building, there's more than one point has hit that roof at different heights. So you then have to work out, as is sort of shown in the bottom right of the slide, which is the most appropriate height to use for your extrusion. So you're going to grow the building to the top of that little chimney, or are you going to grow it to the bottom of the roof, or to the ridge of the roof, or just take an average of all the points. So thinking forward to the other presentation, knowing how your extruded model has been derived is probably quite important. So that's got us level of detail 1. So if you remember, level of detail 1 is a flat roof surface. And it's a very quick way, extrusion is a very quick way to create a rapid data set for the whole city. If you want more detail, so the image we've got here is a church in Sheffield in the UK. If you want more detail, you can actually use that LiDAR point cloud. Again, remember it's 25 centimeters between points, so it's quite detailed, to create roof structures. You can use that ortho photo that I showed you earlier to, again, digitize and create more detailed level of detail to roof structures. You can do this semi-automatically for standard buildings with sloping roofs. Obviously, the structure that I'm showing you, the church that's shown here, requires a lot more manual intervention and manual digitizing to actually get that detail from the model. So I don't know if it's clear on the slides, but the left hand is the 3D city model of the church, and the right hand image is the actual church itself. So as you can see, there's quite a good match between the two. So that's level of detail 2. The next one is level of detail 3, which is essentially the size of the buildings. So obviously things like windows and doors and other structures on the sides of the buildings. And again, aerial photography, but in this case, oblique aerial photography. So in the earlier slides, the images were taken directly above the buildings. Oblique images are taken sort of from an angle, as you can see on the left in that on the slide that you've got in front of you. Is one way of identifying detail on the facades of buildings. You can also take the same principle as you use with LiDAR, so the laser scanning principle, and instead of firing laser from above, you can fire it from ground level and get a very detailed map of the point cloud map of the side of the building. So the one on the image on the right is University College London's Chadwick building. So you can do that as well. Photogrammetry, again, taking stereo images with an overlap of 60%, works just as well on building sides as it does on building roofs. So that's another alternative. The difficulty here, and one of the open challenges here, is that you can get great images. Even if you think of something like Google Street View, you can get great images of the sides of buildings. What's more difficult is to add intelligence to the images, to identify where the doors are, where the windows are, and separate those out as different features within the image. So that's a subject that we're still looking into. So that's level of detail 3. And the 3 steps I've sort of shown you here, the level of detail 1, 2, 3, that would be what a traditional national mapping agency such as the Ordnance Survey would do to create a 3D city model. What I'm going to just move on to now is other alternative sources of 3D that you might want to think about. So the first one in front of you there is a thing called building information modeling, and this has sort of come out of architecture and engineering and computer-aided design, and architects have been using CAD to design and draw 3D buildings for quite a while now, and for new builds particularly, there's a good chance that if it's anything more than a small suburban house, there is a 3D CAD model available. Again, the one you've got in front of you there is the UCL's Chadwick building, and it shows you just the type of detail of both the internal and external structure that you can actually get. So you can get the rooms and the furniture, but you can also get the doors and the windows and things like that. So the upside of that is you get a really good level of detail and you get a really good roof structure. The downside is that you only get this for individual buildings or large infrastructure projects, and you don't get it for a citywide coverage. Because of existing buildings, obviously there isn't citywide coverage of BIM or CAD models. Another source of 3D data, a more simulated source in this case, is a piece of software called the ESRI City Engine, which uses a process called procedural modeling. So again, you can start with a 2D map, and if you don't have the LiDAR data, but you know in a sense how the buildings in your city tend to behave, so you know if they've got a footprint of 100 square meters, they might be 10 meters tall, and if they've got a larger footprint, they might have a different roof structure. You can model this as different procedures in the City Engine modeling program, and rapidly generate a complete city coverage based on your existing street network and your existing 2D data. The result of this is very useful for visualization, but it's worth pointing out that it is realistic, not real. So it's useful more as a visualization tool rather than an actual calculation tool in terms of satellite signals and things like that. For the last two sources of 3D data that I'm going to mention, I'm going to look at crowdsourcing. Crowdsourcing essentially is when the general public contribute data normally via the internet, to a project. They can be from anywhere in the world. They can be from any background in the world. Certainly they don't have to be mapping experts to do this. And there's two different crowdsourcing projects that are relevant to 3D city model creation. Firstly, the one that's been around quite a long while now is a tool called SketchUp, which is offered by Google and allows you to create quite sophisticated 3D models of your own building. And then what you can do is take the data into Google Earth and drape images across it, as you can see in the photograph that you've got there. And you can actually create quite a reasonable looking 3D city model from that. And a lot of these images are available free to download via Google Earth or other sources as well. The issue here is because it's created by the crowd rather than by the National Mapping Agency, there's variation in quality. Some of the models are very detailed, some of them less so. There are some gaps in buildings that shouldn't be there, and so on and so forth. And the final source of 3D data that I think is very well worth mentioning is a project called OpenStreetmap, which is essentially started out as a crowdsourced map of London, because it was very difficult to get official National Mapping Agency data here in the UK, but now has grown to a crowdsourced 2D map of the world, very good coverage in quite a bit of the world, mostly focusing on road networks at the minute and points of interest, so churches, shops, hotels, that kind of thing. But increasingly now they've started to add 3D buildings into that OpenStreetmap data set. It's relatively new, so the coverage and the completeness of how are the buildings all there is actually quite variable at the minute. But again, it's a free-to-use data set of 3D buildings, and you can, of course, contribute buildings yourself into this, this data set. So, my final slide, a quick summary. To create 3D city models at high detail and consistently and good quality is an expensive process if you take the aerial photogrammetry approach. And extracting data is not yet a solved problem. So the bigger research questions that we're looking at in 3D city modeling is, for example, who's going to use the data and what are they going to use it for? And I think we're going to see some examples in the next slides of different uses of 3D data in terms of positioning, and from that, we as 3D people can take interest in, for example, should we actually model the chimneys on buildings? Is that important? Are the windows important? What detail do we actually need? Do we need to know the doors? What scale should we map up? Are we interested in localities or cities or countrywide data sets? How can we extract features more automatically from those point cloud data sets that I mentioned, sort of laser scanning and LiDAR? And also, how important is it to have real data versus the realistic data that you can rapidly create using City Engine? On the plus side, so those are obviously open research questions, which for me are very interesting as a researcher. But on the plus side, as end users, more and more cities now are also publishing their data free of charge to encourage use and to encourage answers to these questions, in a sense, because the more people who use 3D city models, the better we're going to be able to answer the questions that I've just mentioned. So, for example, Berlin, Rotterdam, Toronto, to name a few, you can actually go out and download completely free city models, and again, look at the level of detailed description that I mentioned at the beginning to see exactly what you're going to get inside that model. So that's sort of a general dip your toe into 3D city model creation, and I'll pass you back to Alan.
Thanks very much, Claire. Your presentation generated several questions from the audience, and we will submit it via email, and I want to alert the audience again that you can submit questions to particular speakers or overall to the panel through the button on your webinar screen. And we will get to questions and answers to them in the final quarter hour of the webinar. We turn now to a dual presentation, or a joint presentation, by Gregory Mura of Octal Synthetic Environment and Rahul Gupta of Spirent Communications. The relationship between these two companies is that, at least in the current endeavor, is that Gregory leads the development at Octal of CNAV, or SENAV, a ray tracing simulator that computes the propagation of GNSS signals in urban environments. The new version of this software can be embedded in hardware in the loop process with Spirent SimGen simulator to assess the performance of hardware receivers in constrained environments. I'm going to turn it over to Gregory now. He will speak, and then he will be joined by Rahul toward the end of his segment, and they will cover this area of the field. Gregory, please proceed.
Thank you, Alan. Hello, everybody. So our presentation deals with simulations, and we would like to show you how simulations can help to assess the propagation to assess the performance of the propagation of GNSS signals in constrained environments, such as an urban environment or an urban canyons. Of course, simulation use as an input 3D scenes or 3D mockups. At my company, Octal, we call this mockup synthetic environments. And the realism of these scenes, these 3D scenes, has a tremendous impact on the quality of the return data. And so this is maybe one of the most important issues to solve when you want to simulate the propagation of a GNSS signal in a complex environment. So first of all, let's assume that you have a scene, you are happy with it, and you would like to simulate the propagation and the reception of a GNSS signal in using this scene. So you need to take into account two main issues. First of all, the availability problems. The buildings surrounding the receiver may hide the signal and may prevent the signal from reaching the receiver. So without any buildings, you should have direct rays from the receiver. So it's my dash lines on the left. So it's a line of sight. So it should be the the only signal reaching the receiver if there was no building at all. But unfortunately, when you have buildings, of course, these buildings may prevent the signal from reaching the receiver, and as you might know, you need at least 4 satellites to get a point, to get your location. In urban canyon or in constrained environments, sometimes you will have less than 4 satellites, so you will have availability problems. The localization won't be allowed because there are not enough satellites to compute something. In addition to that, the environment generates multipaths. I mean reflections, diffractions, or transmissions. And so these multipaths are due to the interaction of the signals with the local environments. So that's the reason why you need to model with high accuracy the environment, because it has a tremendous impact on the propagation. So my company is a software editor, and we have developed a software. Its name is SC Nav for navigation, SC for scientific environment. And the software assesses the propagation and the reception of GNSS signals in a 3D scientific environment. So it uses a deterministic method, the ray tracing methods. We have developed our ray tracing kernel using the GPU resources. And this kernel, this method is combined with geometrical optics and uniform theory of diffractions to compute the shadowing effects and the multipath as well. So thanks to this code, you will be able to simulate or to mimic what happens when you have a signal, when you have the propagation of GNSS signal in a given area or in a given environment. So as I told you, and as Claire told you a few minutes ago, the creation and the quality of the 3D scenes is very important. We call these scenes 3D scientific environments. So what is a scientific environment? Well, it's a virtual representation of a real environment. You need to model the geometries, so the shape of the roof, for instance, the height of the walls, the width of the streets, but also the physics. So you need to model the intrinsic parameters of the materials, the atmosphere, because the signal crosses, for instance, the ionosphere or the troposphere. So you need to model it because it will have an impact on the computation. And at Octavicy, and we have sorted environments in 2 types. What we call geotypical environments. So these environments model a realistic environment, but this environment does not exist, but it looks like familiar. For instance, it can be either a European dense cities or mountainous areas. And so it's not a real environment, but it looks familiar. So we have developed software to create very easily such environments. The second type of environment is called geospecific environment. So it models a real environment. So I mean, it could be, for instance, it could be the city of one street of the city of Paris or London, and so it's up to the use case. It depends on your use case to select if you want to use either a geotypical environment or a geospecific environment. Of course, you need to define with accuracy the physics. As we use geometrical optics and uniform theory of diffractions, you need to define the intrinsic parameters, such as the permittivity, the conductivity, the thickness of the walls. So that's very important. As ray tracing is a deterministic method, we can display in 3D the multipath. and their attributes, I mean the power, the received power for each multipass, as well as the delay and the phase are known. So we use geometrical optics to compute reflections and transmissions, and uniform theory of diffractions to compute diffractions on the edge. So the uniform theory of diffraction is an extension of geometrical optics to compute diffractions on the edge. So now, as Alan told you, we have developed an interface between our tool and SimGen, so Spirent's SimGen application software. And it's a real-time interface. So SNAV can be considered as a propagation kernel within a hardware-in-the-loop system. So thanks to these systems, you can assess and you can assess the performance of a real receiver, and you can assess this performance in a real environment. So you only need to have the 3D models of this the 3D sensing environments, and thanks to the coupling between SNAV and SimGen, you will have you will be able to assess the performance of your receiver. So that's what we did, and we have also developed an open loop interface. I mean, SNAV can produce 3D mask, so 3D deterministic mask that can be imported. So it's not a real-time communication. I mean, SNAV will has to produce this mask, and this mask may be imported in SimGen, and it's very useful for instance, for static simulations. If you want to take into account the impact of the surrounding buildings, the buildings surrounding the receiver, you only need this 3D mask if you don't move, to take into account the influence of these buildings on your receiver. Now I would like to show you a 2-minute video. So it's I was advised not to talk during this video in order not to slow down the streaming. So I just would like to say that this video will show you demos of our softwares and of the interface between SNAV and SimGen. This video is shared in 3 parts. The first part show you a simulation along the trajectory, SNAV simulation along trajectories. You have subtitles, so you will be able to read what happens. And the second part is the creation of a 3D mask that can be imported by SimGen, and the third part deals with the interface between SimGen and SNAV. So it's a 2-minute video, and it starts now. Okay. So as I told you, you had the three parts, and so you have seen a dynamic videos, a dynamic simulation along trajectories, and all this signal, all this data can be sent to SimGen, and in order to assess the propagation, to assess the quality or the performance of a given receiver in real time. So now I will leave the floor to Raoul, and he is going to show you, because we have made comparison between real measurement, measured data and simulated data, and he's going to show you the consistencies between these two types of data. So Raoul.
Thank you, Gregory. So expanding on what Gregory was saying, let me set the scene and talk a little bit about what we do at Spirent. So we have hardware and software test solutions that allow the users to simulate GNSS signals and environments at the comfort of the lab. So you can simply connect your GNSS receiver to our hardware and then start testing its performance and optimizing for performance. So when we combine our solution with Octal's SENAV software, we were able to generate more realistic simulation, especially the multipath and the obscuration effects were even more close to what you would observe in the real world. So over here, what you see on the slide pack, we can see the results of our combined simulation. So here, what we are doing is comparing the GNSS performance of a real-life environment and comparing that to what we were able to simulate with our joint software. So we picked a dense urban location. So this was a street in Toulouse called Remusat, and we placed a receiver there at a fixed location for 15 minutes and recorded the GNSS receiver data to analyze later. We then came back into the lab and then simulated the similar environment using the Spirent and Octal SENAV software and hardware. The fact that it was a challenging location, the receiver only reported about 4 line-of-sight signals, and the rest were refractions and diffractions. So this caused the receiver to report roughly 9 to 18 meters of error compared to the reference location where it was. So you can see that on the top left-hand side of the slide. The simulated results, as you can see on the right-hand side, look very similar, where you can see the reported error by the same receiver was in around 7 to 15 meters of error that are reported. What you see in the bottom right-hand corner is the position drift that the receiver reported if you just compare the live data versus the simulated data. Again, when you look at those two comparisons, you can see there is a very close correlation between the real life environment and also what you could do with the simulation. So in summary, when you combine the 3D modeling techniques with the simulation techniques of Spirent, you're able to generate a much more realistic environment, and that allows you to test the GNSS receiver and even optimize it in the comfort of your lab. So we have more videos available if you want to find out more about the SENAV software. So you can click onto YouTube and find more information. Or if you have more specific questions, then you can reach out to Gregory or myself. Over to you, Alan.
Thank you, Rahul and Gregory. We turn now to Paul Groves, who will talk about, we've been talking about the collection and evaluation of data. Paul will now take us into the actual application of such data for better GNSS positioning. And I want to alert our audience that we will go a few minutes over the hour. We'll have questions and answers following Paul's talk, and to allow ample time for that, we will go a little bit past the top of the hour. Paul, over to you.
Okay, hello everybody. I'm going to talk about how we use enhanced 3D mapping to get better performance from GNSS in dense urban areas. So The problem with GNSS in urban canyons is we have lots of buildings blocking reception of the signals. So they particularly block signals coming from the across-street direction, leaving some satellites coming from the along-street direction. So in theory, we can get a reasonable accuracy along the street, but poor accuracy across the street due to the geometry problem. Unfortunately, it's not that simple. As well as signals being blocked, we also have reflected signals. And if you receive a signal via a reflected path, that path delay causes a positioning error. And with conventional GNSS equipment, we don't necessarily know which are the direct signals and which are the reflected signals. So with a conventional solution in urban areas, we can have errors of tens of meters, sometimes position errors exceeding 50 meters. Now, if we have 3D mapping, we now have the advantage that we know where the buildings are. We also know the height of the terrain, which we can also use to aid positioning. So using a number of techniques, it's been shown that using 3D city models to aid GNSS, we can get positioning errors of 2 meters under good conditions, maybe 5 meters under not so good conditions. So how do we do that? Well, there are 3 main ways in which we can aid GNSS using 3D mapping. There's height aiding, there's model-aided ranging, and there's shadow matching. And I'm going to tell you a little bit about each technique and present a few results that we have. So, with height aiding, if we know the height of the terrain below us from 3D mapping, we then know the distance from us to the center of the Earth. So effectively, we have an additional virtual ranging measurement that's going from the center of the Earth to us. And unlike the conventional GNSS ranging measurements, we don't have to worry about time synchronization. We don't have to worry about atmospheric errors. So it's an accurate measurement, and it's coming from a completely different direction from all of from the conventional GNSS signals. So that dramatically improves our positioning geometry. Now, in an open environment, this height aiding only improves vertical positioning. But in a constrained environment where we've got a problem with signal geometry, we've found that the height aiding can also dramatically improve our horizontal positioning, as these results here show you. So for these tests, we set up a Leica Viva surveying GNSS receiver at about 20 or so locations in the financial district of London, where the buildings are very dense. And we computed positioning solutions with and without terrain aiding. And we were finding, with no terrain aiding, position errors were around 50 meters. But bringing in the terrain aiding improved vertical positioning, as we would expect, dramatically by a factor of 5. But we also improved the horizontal positioning by about a factor of 2. So terrain height aiding is well worth doing in dense urban areas. The next thing you can use 3D mapping for is to predict which satellite signals are received via direct line of sight and which are received via a non-line of sight path, so the reflected signal only. So you can use ray tracing techniques, as Rahul and Gregory showed you, or you can use graphics processing techniques to determine which signals take what path. So you can then predict which signals are line of sight, which signals are non-line of sight, and you can use that to improve GNSS positioning. So this process can be computationally intensive. So at UCL, we've developed a technique for speeding things up, where what we do is we use the 3D city model to compute a series of building boundaries, essentially like sky plots for a series of positions. We store those building boundaries, and then we can determine whether a satellite is non-line of sight or line of sight just by comparing the satellite elevation with the building boundary at the appropriate azimuth at a range of different positions and feed that information into our GNSS positioning algorithms. So this enables these techniques to run in real time with relatively modest processing. For example, we've ran shadow matching on a standard smartphone. The disadvantage is the building boundaries could potentially take up more memory or more data storage than the 3D city model. So if we're using our line of sight and non-line of sight predictions to aid conventional ranging-based GNSS positioning, there's a number of different ways in which it can be done. So, for example, we can consider a single candidate position if we know roughly where we are, or we can consider multiple candidate positions if our position uncertainty is several tens of meters. And obviously, considering more candidate positions increases our processing load. We can also merely predict whether a signal is non-line of sight, or we can go one step further and try and predict the correction required for reflected signals. And if we're again predicting corrections, that requires more processing loads. So the approach that we're running at UCL at the moment is to stick just to non-line of sight prediction and to consider multiple candidate positions. And in the GPS World article coming up next month from LiDAR Husu, you can see their approach for the processor-intensive non-line of sight correction at multiple candidate positions. So our results with the non-line of sight prediction and our early algorithm is we've found that we have a 20% improvement in horizontal positioning, and we have a vertical positioning improvement of 13%. So we have some improvement. We have an idea for another algorithm that we're going to implement over the next few months, and we hope that using our new algorithm we'll get a further improvement. Now, our third way of using 3D models to aid GNSS positioning is shadow matching. So remember, in the cross-street direction, conventional GNSS positioning is poor in dense urban areas. So what we need is a new approach. So with shadow matching, what we do is, if we have a 3D city model, we can, and of course we know the elevation of the satellite. We know that if we can receive a direct signal from the satellite, we're in one area of the street. And if we can't receive a direct signal, we're in another part of the street. And then you can repeat that process with another satellite to refine your position further. And then using several satellites and determining which ones we can directly observe, you can determine where along the street you are. And then that enables our non-line of sight and even untracked satellites to contribute to our positioning solution. So in our implementation of shadow matching, we have a 5-step algorithm. So first of all, we use a conventional GNSS position solution to determine a search area, and we've been working with a 40-meter radius. So within that search area, we have an array of candidate positions, and using our 3D mapping or building boundaries, we predict satellite visibility at each of our possible positions. At the same time, we use the signal-to-noise measurements from the GNSS receiver to observe our satellite visibility. So depending on the signal-to-noise, we estimate a probability that we're observing the signal direct. And then by comparing our observations with predictions, we can score each position hypothesis, and from that we determine position. If you look at the multicolored diagram on the right of your slide, what you're seeing is the score for each candidate position. So red areas are high scoring, blue areas are low scoring, white areas are areas we've eliminated. So they're either areas where we know that they're indoors and we already know that we're outdoors, and they're the areas outside our search area. And then finally the X on the slide, that marks our true position. So that you can see with shadow matching, you've got a large red area on the same side of the street as our X. So shadow matching is telling us what side of the street we're on. In terms of the along street positioning, it's not so good, but it doesn't matter because the geometry is such that our conventional ranging-based GNSS solution will work better in the along street direction. So our two solutions are complementary to each other. So now we have some results for you from last year. So these are some results on the move. So my colleague Lei Wang, he walked 4 different routes in central London, and we compared the cross-street positioning performance of 3 solutions. So the conventional GNSS solution was accurate to about 11 meters. Computing a separate shadow matching solution at each position was accurate to 6.5 meters across the street, but using a particle filter to combine shadow matching information from multiple epochs, that gave us a position accurate to 2.5 meters, which is pretty good. So our next steps are to integrate everything together into one system, and to look at ways of improving the reliability so that we get our optimum performance as much of the time as possible. So for more information, you can see our recent papers on our website. If you're interested in our forthcoming papers at the September ION conference, send me an email. And I finally like to thank my colleagues, Doctors Munir Ajrad, Lei Wang, Claire Ilul, Zi Jiang, and Professor Marek Zebart. Over to you, Alan.
All right, thank you, Paul. Now for the question and answer period, and again, we're going to go, we've received several questions. I'd like to get to at least 4 of them if we can in the time remaining, and I'm going to extend the time remaining to do so. So stay tuned past the top of the hour. First question, I'm going to ask it. I'm going to add a little comment of my own, and then I'll throw it open to any of the 4 panelists who wish to answer. And this question comes from someone who asks, what is the future of GNSS in these applications after some major ongoing advancement in imaging technology? There are several companies, especially UAV companies, who do not rely on professional-grade GNSS for positioning. They have advanced image processing engines which only need commercial-grade GPS for the reference. Now, I think that obviously this evidences a lot of interest in UAVs, which is, shall we say, rampant in the field. And with UAVs flying with greater frequency, as may soon be the case, I think some people are anticipating that there's going to be a lot more aerial imagery and data available. So why do we need to do all this? If we're going to have this wealth of images, why do we need to do all this? And I think I have an opinion on this, but I think our panelists will have a more expert opinion on it. And please, any one of you, feel free to answer.
So maybe I'll start by talking a little bit about the imagery that's coming out of UAVs. There is certainly a lot more of it, and certainly we have research projects here at UCL making use of UAVs to create maps in areas like the Congo, where there isn't good mapping data and good aerial imagery. But the quality of the camera used on a UAV at the minute, because it needs to be particularly lightweight, doesn't necessarily match the quality of a camera used in a commercial grade aerial photogrammetry capture exercise, such as the Ordnance Survey would carry out. I guess another thing to consider when you're thinking about UAVs is coverage. Again, if you're the national mapping agency, you've got a responsibility to cover the entire country. Whereas if you're doing a UAV project, you're going to cover obviously just the areas that you need, which isn't necessarily a bad thing. But again, then you have to have the skill to post-process those images, create the ortho images that I showed at the beginning of my slides, and use the specialist software to extract features and then create a 3D city model from the imagery. It's not that it's not possible. Certainly with the right skills and the right software it can be done, but it's not something that as yet is open to everybody to do in terms of getting the crowd, as it were, to do all of this relatively complex exercise. Potentially in future, in 5–10 years, it might be far simpler and far more streamlined, but I don't see that happening right at the minute.
Anyone else want to weigh in on that before we proceed to the next question? All right. We'll go to the second question. One of our listeners is clearly impatient to get out and start doing some of this stuff. And they ask, could you please give examples of innovative applications using GNSS positioning such as this that could be implemented by city authorities, municipalities, regional governments, and so on? How do we actually get this research into practical application, or where might it be practically applied?
Hi everyone. There are a few applications we've been thinking of for this kind of work. We're particularly thinking of initially more professional applications to get the field moving before things move on to consumers. So one of the applications is navigation and guidance for the blind and visually impaired. So the positioning system needs to be accurate in urban areas to identify what side of the street somebody is on and which building they're in front of, and then you can use separate maybe guidance technology, maybe based on imaging or radar, to guide people into a building, but we need our positioning technology to identify which building that is. Another application is intelligent transport systems, where we may have a control center guiding individual vehicles in busy cities, and for there you need a positioning system that's good enough to tell you which traffic lane a vehicle's in. And similarly for advanced rail signaling applications, maybe then there's augmented reality. If your positioning solution is more accurate, it's easier to initialize the visual system. And then finally, mobile mapping. Researchers like to collect mapping data about pollution levels in cities, or mapping accessibility for disabled people. And if we can get a basic GNSS position solution in cities of a few meters instead of the tens of meters that we have today, that can be done cheaply, easily, and cost effectively. And then I think after these applications, if they're running successfully, then that might push things forward to consumer applications.
Thanks, Paul. The third question, or a couple of questions actually, that are somewhat related, going to go to Gregory and Rahul if he wishes to also. One listener writes, my question relates to whether CNAV takes into account the presence of users and vehicles, for example, such as buses, and their effect on the propagation of the signal to the antenna of the receiver. And secondly, is the interface of CNAV and SimGen data done on static data, such as snapshots, or in dynamic mode, such as continuous data collected on board a moving vehicle? Gregory?
Yes, Alan, if you don't mind, I would like to say something else to answer to question 2. Just a few information. My company, Octalesi, has created an association is one of the founders of the association guide. So this association is a French association to gather all GNSS skills And the Guide Association is involved in a European project, a H2020 project. The name of the project is Jupiter. And I'm involved in this project, and one of my tasks was to write and to create a presentation dealing with applications and the advantage of using European GNSS for applications. So I can send these slides to the audience, and also this presentation will be shown during the next ITS conference in Bordeaux in October, Bordeaux, France in October. So for the first question, dealing with SCNAV. So with the current version of the interface between SCNAV and SIMGEN, it is not possible to have moving vehicles such as pedestrian or bus. But it will be done in the next version, as there is no technical issues. We just have to upgrade a little bit our retracing kernel in order to take into account moving obstacles or moving clusters of triangles, because our retracing kernel use mesh objects. So we have to update this, but we do not see any problems dealing with moving vehicles. Certain questions, of course, it's a dynamic mode. I mean, it's a real-time mode, a real-time interface between SCNAV and SIMGEN. So the continuous data collected on board of vehicle can be transmitted and can be computed in real time.
And just to add to what Gregory said, so both for static vehicles and dynamic vehicles, it should be possible to simulate the environment with SENAV inspired simulators.
Yes.
No, all right, thank you. We're going a little past the hour. We have one more question. I see that the attendance is holding steady, so everybody is finding this of interest. And just one more question for our panel, which again, a combination of questions from several listeners showing a common interest in taking this data and these models a step further into the driving mode. A lot of preoccupation with autonomous vehicles and driving and so forth. So I'm going to read all three questions all together and then throw it open to our panel. How can we ensure the integrity of the resulting maps or provide an index of quality if these are to be used for critical situations like autonomous driving? Someone else asks, effective maintenance strategies for these databases and models. Will the models piggyback off of or aggregate the models created by self-driving cars? And they mention PHODAR, P-H-O-D-A-R, derived from Street View databases. And finally, when developing the models used to impact GNSS signals, how are they validated? So overall preoccupation or concern about the validity and integrity of the data, particularly for driving. Panelists? Okay, so I'm thinking from the perspective of the positioning algorithms, and we can't assume that the maps are going to be perfect. Buildings are knocked down, new buildings are put in their place. Particularly during construction, it's difficult to keep a map up to date. And we also have the bus problem. In London we have big double-decker buses. They're going to disrupt GNSS signals, and you can never include that on the map. So we have to work on the principle that some of the predictions we make from our 3D mapping are going to be wrong. So what can we do about it? And we need some kind of integrity monitoring. We need a kind of RAIM approach for shadow matching as well as for conventional ranging-based GNSS. And I had a bit of a think about that. There's some ideas in our ION paper coming up, so I won't talk about that now. But an interesting feature of
shadow much integrity monitoring with 3D models is that the same modeling error, whether it's an unexpected building or a bus, can affect multiple GNSS signals. So when you're considering a potential error in one signal, you also have to look at other signals with very similar azimuth angles, and they could be affected by the same problem. So it's an interesting research challenge to keep us all busy.
I think maybe to add something small to that, just thinking about the self-driving cars as well, there's certainly the potential to combine data from self-driving cars with existing 3D city models to improve those models. I guess the challenge there is eliminating these moving vehicles that will, in the sense of the self-driving car is essentially scanning the neighborhood. If there's a vehicle, that vehicle will form part of the scan. If there's a person walking on the sidewalk, that will form part of the scan as well. So before you start looking at the buildings or the static elements of the city model, you need to first eliminate the dynamic elements from the scans from the self-driving cars. Just a sort of short comment about quality of data as well. Theoretically, any data set that you use should be very well documented to tell you we've used this particular roof height or this particular density of LiDAR points and so on and so forth. But that's very much theoretical. In practice, I think it's presentations like the ones we've been listening to today that raise awareness in the community that just because you have a city model, it absolutely doesn't mean it's perfect. And anything any positional information derived from it needs to take that into account, just as Paul was saying.
All right. Thank you, Claire and Paul. We're going to wind up the webinar now. I want to thank everyone in the audience for staying with us a little bit past the hour. We had quite compelling content, and I want to thank everyone in the audience for submitting such interesting questions. Joelle will return in a moment to tell you when the download of this webinar will be available, so you can forward the link to colleagues who you think may find it of interest. And I think it's quite possible that we will, in some months' time, recapture some of this content in either print or an e-newsletter. So it will be available that way as well. I want to thank all of our panelists, Claire Elul and Paul Groves from University College London, Gregory Mura from Octal SE, and Rahul Gupta from Spirent. And this is Alan Cameron from GPS World. Thanks again for attending this webinar. We'll have another one the next one coming up on August 20th, and that will have a wireless focus. I'm talking now with speakers and hammering out an exact topic. Look for news of it on the website very shortly. Thanks very much, and goodbye from GPS World. Over to Joelle.
Thanks again, everyone, for attending our webinar. A recording of this webinar will be posted to the GPS World website and will also be emailed to you tomorrow. We do have another webinar scheduled next week, sponsored by Hemisphere. It is titled New Generation GNSS Solutions, Precise Positioning, Navigation, and Applications. That's next Thursday, July 23rd. Please visit gpsworld.com/webinars to register. And thanks for attending.